Assalamualaikum and good day class. Now we move on to chapter 3, Thermal Treatment and Metallic Material. This chapter is overall 8 hours duration. In this chapter, we shall learn all about heat treatment. First is subchapter 3.1, Time Temperature Transformation Diagram, or what we call as TTT diagram. We will learn about the products of cooling austenite, what are the resultant microstructures that can be constructed after you cool the austenite. And we also will learn the factor affecting the position of TTT diagram. In 3.2, we shall learn about the heat treatment of ferrous metal. There are a few heat treatments that are important in this subchapter, such as annealing, normalizing, quenching or hardening, and lastly, tempering. And in the subchapter of 3.3, we shall learn about the hardenability of steel. What is the hardenability curve? And the resultant microstructure of hardened steel, which is martensite. After completing this chapter, you should be able to explain what are the principles of heat treatment and explain the difference among the various kind of heat treatment processes according to the TTT diagram, type of microstructure that are resulted from the heat treatment, and the effect of heat treatment in terms of the hardenability. First is the subchapter 3.1, Time Temperature Transformation Diagram. At the end of this chapter, you should be able to understand what is the TTT diagram, and you should be able to sketch the temperature time path to produce specific microstructures according to certain time and certain temperature. So what is the TTT diagram or time temperature transformation diagram? The TTT diagram is also known as the isothermal transformation or Bain S-curve diagram. What does the TTT diagram portray? It actually gives the kinetic of isothermal transformation. It shows how the microstructure evolve or changes due to kinetic energy given by the time and temperature. And it shows the effect of time temperature on the microstructure of steel. Different time and different temperature will give different steel microstructures. Other than that, the TTT diagram also will show the percentage of transformation. For example, how many martensite or how many percentage of pearlite that can be constructed if you heat the steel in certain temperature and time. And the TTT diagram also will show you the extent of transformation, whether it is transformed isothermally at certain temperature. It means that you shall know after certain curve it will change to other type of microstructures. In the previous chapter, you had learned about the iron-iron carbide phase diagram. So according to certain composition of carbon, the microstructure will change accordingly according to the applied temperature. So why you use the TTT diagram in this chapter? It is because the iron-iron carbide phase diagram shows no time axis. You only know the composition and the temperature. You don't know how long you shall heat your material or your steel or your iron at certain temperature and certain composition. So, to show the transformation of the microstructure, especially for martensite and binite structure that was not in the iron carbide phase diagram, we shall use the TTT diagram. And we also use the TTT diagram to determine the microstructure produced in steel at various rate of cooling. So different kind of cooling rate will produce different microstructures. And the TTT diagram is also used to plot temperature versus time for steel and alloy at certain composition. For example, 1% carbon, 3% carbon, 6.7% carbon, or 0.022% carbon, which is all you already learned in the iron-iron carbide phase diagram. Now, look at the curve here. So this is the curve of TTT diagram. As you can see, it has a C shape in it, and you could easily understand it by using the phase transformation concept. Look at this diagram over here. So this over the y-axis is actually the temperature, and the x-axis is the time. And you could see the transformation curve, okay, being determined by the percentage of the microstructure. For example, over here is 0.01%. Okay, over here, up here, we have austenite. Okay, and then we have 50% or 0.5% perlite, and you have perlite up here and binite up down here. So it depending on the percentage, the time, okay, the temperature, and also the composition. It is easy to see the temperature in which the transformation of the kinetic is fastest. And this is called as the nose of the TTT diagram, denoted by this red dot. So here we call it as the nose. So the generation of the TTT diagram. So you have your iron-iron carbide phase diagram, in which what you learned before. You know that in the iron-iron carbide diagram, okay, at the eutectic, okay, the CO is 0.76 at the transformation temperature of 675 degrees C. So here is your iron-iron carbide phase diagram. Okay, so you transform it into a TTT diagram. So in the TTT diagram, okay, at the temperature of 675 over here, okay, and you shall see that there are few phase transformation. The first phase in the left is austenite, okay, and then it is transformed into perlite. So in the middle here, we have 50% austenite and 50% perlite. Okay, so that is how you transform, okay, the diagram from the iron-iron carbide phase diagram into the TTT diagram. Okay, so how or where does the transformation, okay, begins and transform? Okay, two solid curves are plotted. You have the first solid curve, okay, at this red, denoted by this red line, and you have another solid curve denoted by the green line. Okay, so the line where the transformation begins is actually this line, okay, at the temperature of 675 just now, okay, and at the time of, okay, at the time, you can see that the time over here is the same as the iron carbide phase diagram, okay. But in the iron carbide phase diagram, you can see that you don't know, okay, the time, because what it shows actually is only the composition and the temperature. So if you want to know the time, you have to use the TTT diagram. So okay, so you bring it down and to over here, and there are time where the transformation ends over here, so you bring it down to here. And if you want to know, okay, so where the transformation begin is where the austenite, okay, begin to transform into something else, which is pearlite. So you have here 100% austenite, and then okay, when it move here, okay, the austenite will begin to decrease and the pearlite will begin to increase, okay, until it reach this point where you have 50% austenite and 50% pearlite. And as you move on to the right, okay, in the green lane, okay, you will have 100% pearlite with 0% austenite, okay. So that is how the isothermal transformation diagram were created, okay. Generally, okay, the austenite to pearlite transformation will only occurs, okay, this is very important, okay, austenite will transform into pearlite, okay, only if the alloy are super cool to below eutectoid temperature. So first, okay, the first process is to increase the temperature, okay, at the temperature above 727, which is above the eutectoid temperature over here. And then after you increase the temperature above the eutectoid temperature, then only you shall decrease, okay, you shall reduce the temperature, you shall cool your material below the eutectoid temperature, then only the austenite can transform into pearlite. Okay, I hope you understand the concept. Okay, next, okay, so the isothermal transformation diagram, okay, it can only occurs, okay, when the composition is at the eutectoid composition, which is 0.76%. This you can get it, you can refer it into the iron carbide phase diagram before, okay. And okay, this S curve, okay, this TTT diagram could only be transformed if only, okay, the heating temperature, okay, your material is heated, okay, above the eutectoid temperature, which is above 727 degrees Celsius. And then, okay, if you want to transform it, the austenite to the first, okay, to the first microstructure, okay, you have a few microstructure over here. The first one that you will went through is the pearlite. If you want to transform it to pearlite, then you have to rapidly cool it to 625 and hold it, okay. You have to hold the temperature, okay, first, okay, heat it above 727 and then reduce it, okay, to 625 degrees Celsius, and you have to hold it, okay, hold it until it reach the pearlite region, okay. So that is how it occurs. that is how the austenite transforms to pearlite. Now, let us look deeper in what is happening during the isothermal transformation diagram. So you have line A, B, line B, C, and line C, D. So the line AB is actually indicating the rapid cooling of austenite. So austenite, okay, after you heat it over here, so all this area is actually the area of austenite. Okay, so above 727, the austenite is stable. Below 727, the austenite is unstable. So when the austenite is unstable, it is transformed into another microstructures. Okay, so the first line is where the austenite is rapidly cooled. And then you have the line BC, where you hold the microstructures until, okay, it reach the line where, okay, where the austenite will begin to transform into another structure. Okay, so horizontal line CD will mark the beginning and the end of the isothermal transformation. So what is the meaning of isothermal? Okay, iso meaning one, thermal meaning heat. So it means that the temperature will remain or will stay constant or will stay the same along the transformation. Okay, so the point C is where the transformation of austenite will begin. Okay, so it will transform to pearlite, okay, bit by bit. And the point D is where the transformation is complete, meaning to say it is completely transformed to pearlite. Okay, so let us look at the example of cooling austenite, which is the first example. Okay, so you have your question over here. Specimen is rapidly cooled to 650, hold for 500 seconds, and quench to room temperature. So remember, the first step is to increase the temperature above 727 or the detected temperature. Okay, this question will ask you how to draw. Okay, how to first draw. If you want to know the resultant of final microstructure, you have to first draw. Okay, so drawing the TTT curve, okay, or TTT graph according to the question. So the first step is to increase, okay, the temperature. So here is your sample. You put your sample inside a furnace or oven and you heat it above 727 until it reaches the point. Okay, the same point as before. Okay, the same point A, B before. Okay, and then you shall reduce. Okay, after it reach above 727. Okay, you shall reduce it, okay, to 650. Okay, but okay, you shall put it, okay, you shall put it at the area of unstable austenite. Okay, this area. Okay, anywhere around this area. Okay, and hold it for 500 seconds. So 500 seconds is actually between 100 and 1000. So over here. And quench. What do you mean by quench? Quench is actually reducing the temperature. Okay, put it or slowly reducing the temperature, so the temperature will slowly reduce to room temperature. So when you off your oven, okay, it will slowly, okay, the temperature will slowly move, okay, downward until it reach the room temperature. So okay, as you can see, when you hold it to 500 seconds, okay, so it will become 100% perlite. So here, over here. So that is the product of cooling austenite, which is 100% perlite. So you have A over here is austenite. You have B over here is perlite. B is bainite. And M is martensite. So that are all, okay, the type of microstructure that can be produced as a result of you cooling the austenite. Okay. After you heat your material above the eutectoid temperature and you reduce the temperature, the first microstructure that can be produced is perlite. So this is the morphology or how the perlite look like. There are two perlite that can be produced. The first one is coarse perlite and the second one is fine perlite. Coarse perlite is produced at temperature just below the eutectoid temperature. Okay, with larger temperature, it diffuses faster, so the perlite produced is coarser. So generally, smaller temperature variation will produce large colonies of perlite. And if it is transferred way below the eutectoid temperature, okay, small temperature will produce slower diffusion, so the perlite that is produced is much more finer or much more smaller. So generally, larger temperature variation, meaning to say if it is cooled way lower, then the colonies are smaller. So generally, we can conclude that coarse perlite is formed at higher temperature, and because it has coarser structure, it is relatively softer, while fine perlite is formed at lower temperature and it is relatively harder. I think that is all class for today, and we shall move on to another type of morphology in the next class, which is bainite, martensite, sphaeroidite, and many more. Thank you, class, for your attention.